Good afternoon, everyone, and thank you guys for having me. My name is Ben, and I am not from North Carolina. I am from Washington, D.C., where my primary job is actually at the University of Maryland in the computer science department. But I'm here today representing District Data Labs, which in DC is an open source collaborative. There are probably 20, 30 people who are involved in the organization that work on open source projects. And so today I want to talk about a few of those projects and do something a little different. Take off the computer science hat that I usually wear and start thinking about the analytics hat. When we develop software, we're developing it usually for analytics users, and to sort of think about how we can combine computer science, graph theory, graph analysis, and graph databases or data structures with a more analytical focus, particularly looking at time series, trend analysis, and predictions. So, these are just some thoughts from the work that we've been doing and the research that we've been looking at, and I hope that you guys enjoy it. Just one note. Most of the software that I present here is going to be developed by DDL, things like Bailey and Minky. They're all on GitHub, they're all open source, so unfortunately I didn't get links into the presentation, but please tweet at us, let us know if you're interested in these things. But I also chose to use, for the graph library, I chose to use Graph Tool. Which I think is sort of a lesser known, almost everyone knows about NetworkX, but Graph Tool is this sort of, it's a C++ implementation of a lot of libraries with a Python interface, and it's hugely powerful and also a giant pain in the butt. So forced myself to grapple with that so we could explore, maybe using this tool, and all the code is from Graph Tool that you'll see in the presentation today. So the question that I want to ask is, are graphs effective for analytics? Right? I'm a computer scientist, and we are told, at least in computer science, that graphs are sort of this very useful data structure, and you can formulate algorithms as graphs, and you can sort of think about traversals. When we teach Computer Science 131 at the University of Maryland, right, all these undergraduates are learning to program, and their first implementations are Dijkstra's algorithm and the Bengfort algorithm. So like right out of the gate, they're programming graph-style computations, and they sort of invade the world. But when we started looking at the analytics, a new question came up, like, should we use graphs at all when perhaps linear algebra implementations or machine learning or other statistical styles of analysis are more sort of mainstream, particularly for things like time series analysis. So I hope to explore that with you guys today. So, just actually out of curiosity, who here does use graphs for analysis? Okay, so that looked like a small sample, maybe 10%. And, even as we're starting to look at this presentation, the thing that I've realized is it's actually not that straightforward. Even though it's a simple sort of thing to get into, it really does have a lot of different types of implications. So when I think about graphs and when I teach graphs, I usually present two facets, right? Graphs are good for either algorithmic performance, particularly for machine learning. And the reason that they're good for algorithms is because they have very simple or understandable implementations. And when you have something that's very easy to understand, you can optimize it, and you can do more complex things, leveraging that simplicity to great advantage. The other key point here, and I think this is why graphs exist in computer science, is that graphs are natively parallelizable. Right? So you can distribute them using GAS, gather, analyze, scatter. You can bundle nodes and their neighborhoods in a MapReduce fashion. There are many different distributed computing libraries like GraphX and Pregel and things for doing large-scale computation on graphs. So at sort of all levels, we think about that performance benefit. But then on the other side, graphs are also very useful for visual analytics, right? Humans are well trained to think about interconnection structures because we are social creatures, and we can immediately recognize and get insights from very simple graphs, right? They're immediately understandable. And they actually provide a mechanism for interaction that's not native to other types of visualization. When you see a graph, the first thing you want to do is touch it and move it and sort of see what's changing and how things are being connected and dragged around the screen. And I think for that reason, graphs have played a large role in data storytelling, data narratives. Mike Bostock has popularized them at the New York Times and other places. So we have these sort of like two ideas, like graphs should be very useful. So what can you do with graphs? What types of analyses can you do? I think about things in terms of four sort of primary classes of computation. The first is computation, right, or construction rather. Can we build a graph? Can we build a graph out of another graph, or is there the possibility, given some constraints, that you can organize nodes and their relationships together in a meaningful way? Once you've constructed it, you can start asking questions like, is there a formal structure to this graph? Is it a bipartite graph? Do cyclicities exist? Is it fully connected, not connected at all? And so even just the act of building or constructing a graph is an analytic process. We're talking about statistics today, maybe a statistical analysis. So once you have a graph, you want to start counting things, start enumerating things, particularly degree. How connected are these vertices, right? How many edges are there, right? Do we see bundles or clusters or triangles, right? What are the things that we can count in this graph and perform other types of statistical analysis on? And that style of enumeration leads to most machine learning implementations, particularly when you think about graphs, things like PageRank and even sort of Bayesian network analysis or probability mechanisms. You can ask about existence, right? Is there a minimum spanning tree? What is the shortest path? Is there a collection of vertices that meets this criteria? When you start thinking about that, you can actually start to think, well, maybe there are structured style queries that we can perform on graphs. And in fact, there are a lot of attempts, Cypher, Datalog, even sort of SQL-like query languages to say, hey, can we do something with graphs in a more structured or declarative fashion? But whereas that's the end, right? Some table or some result is the end of an existence query in a structured domain. With graphs, you can also start to think about optimization, right? What's the shortest? What's the longest? What's the minimum? What's the fastest? And you can start to develop, iterative approaches to understanding these things. So what are you actually doing? The primary method of computation is traversal, right? You think about where you start and where you're going, how do you cross these edges, and I think that might be the first place where we have to do a shift, right? Instead of selecting or gathering, we have to think about moving, right? And sort of like when you're on a terminal for the first time, you have to think, well, where am I? One of my colleagues mentioned that this figure sort of looks like a geographic map, right? Maybe road network or something like that. And that's a really good thing to have in your head, because every one of those four classes, all of the algorithms that are inside of those classes of graph analysis are implemented as traversals, right? You collect edges and then you move out, or you collect nodes and you move out their outgoing edges and keep going through. So if you want to traverse on something, we do need some sort of model, right? Some graph model, and the one that I'm going to, sorry, out of order slide there. The one I'm going to talk about today is the property graph model. So property graphs are separate from adjacency lists and other style graphs that you might have. And I think they're important for data scientists because property graphs are really the only graph model that actually embed data that's usable inside of them. So property graph thinks about all structural elements, right? And all structural elements can have associated key value pairs, and they also all have to have a unique ID associated with them. Now, I'm using that term structural element deliberately vague for a reason, because once we start adding dynamics, once we start adding change, what is a structure becomes very important. So just to list a few, the graph itself is a structure, right? Whether it is the complete graph or a subgraph or some picture at a piece of time, the graph should be able to have key value properties associated with it. And then that structure itself is an object that contains both vertices and edges, very specific set of vertices and edges. A graph might be the result of a query, right? You might think of it that way. I've been using these terms. Hopefully you guys are familiar at least a little bit with vertices. Vertices are objects that have incoming and outgoing edges. And again, that deliberately vague sort of description gives us the opportunity to model a lot of things as vertices, not just entities or things, right? They are just simply structures that have connectivity associated with them. And what are the connections? Those things are edges. Edges are simply things with a source and a target, right? An incoming or an outgoing edge, they can be directed or undirected, but they connect vertices in particular. So, as you can see here on this sort of property graph, this demonstrates the Olympics. We have several different types of nodes. We have country nodes, we have athlete nodes, we have event nodes. We even have the Olympics itself as a vertex here. You can sort of think of this as a graph of the 2016 Olympics, right? But there are other Olympics. So, even just coming up with some graph model to show you that doesn't even necessarily have time in it might embed time, right? This is a single graph that doesn't represent the entirety of the Olympics. Vertices have types, right? So if we're going to start to do multi-domain modeling, you're going to have a type. Edges have labels and potentially also weights, right? But these are very rich data structures, and they allow us to model time, I think very easily. And just to go back to this quote from Marco Rodriguez, Marco is the contributor to Apache Tinkerpop and DataStax. He does a lot of work with graphs, and I would call him a graph evangelist, right? He really pushes the use of graphs in everyday computing and data analytics. But he summarizes those sort of two elements, algorithmic performance and visual analytics, as graph technologies ease modeling in the domain, right? Because we're good at coming up with interconnection instructions, but that modeling itself isn't enough, right? The ability to model something isn't, if you have a weak model, it's not going to get you very far. So what graphs also do is they ease the speed and simplicity of the types of queries that you're going to ask of them. And so we want to investigate that very specifically with time today, right? Is that actually true? Can we get away with more than just having a graph model? And so we should ask ourselves, in this property graph data structure that we have, how do we model time? Where do we put time in this? So I want to start with, where is the time in a relational database, right? I've already sort of made this parallel to structured queries and the sort of first step at analytics where we try to materialize some table, some list of tuples that we can start to perform work on. So if you're going to model data in a relational database, particularly if it's normalized, you're going to usually think of entity relationship diagrams, right? So great, we have a graph right off the bat. When you think about entities usually have descriptive time elements, right? They're dates or times. They're usually encoded as a timestamp with time zone if you have a Postgres database. And those things change, right? And a descriptive date time will change on an entity using it like a transaction will update those records. If you want to encode a series, right, you want to save history or think about how things change over time, you need to actually create a special type of entity called an event. Events are tables that are optimized for inserts, right? You write to them, you don't modify them. For that reason, there's been a lot of work in time series databases specifically, like InfluxDB and a few others, where they're trying to, create these sort of really read-through throughput databases that can handle a lot of event encoding. Events, though, themselves are going to be discrete, right? They're going to have, if they have a single time step, they just represent a single point in time. And if you have two time steps, then maybe you can represent an interval. But you can't encode time on a single relationship, right? You can't encode a foreign key with time. And if you want to do that, you have to create some sort of intermediate table, right? A relational table, which we usually sort of think of for many-to-many type relationships, not one-to-many or even one-to-one type relationships. So even as we start thinking about this from the relational perspective, we're already sort of bogged down in a lot of details that hopefully you guys can see immediately we get away from with the property graph model. Just as sort of a side note, if any of you guys have a relational database that has this kind of data, I would encourage you to think about GraphGen, another open source tool that can extract graphs out of relational databases and do in-memory graph computations, which is a pretty neat tool. Okay, so back to the property graph model, we were going to want to embed time as a property, right? That seems pretty clear. And where time gets embedded is at any particular structure, right? Any key value pair. And you can start to see that there are a lot of different types of embedded time. So here across the top, we have a couple of these sort of these blocks with ABC having last seen descriptive time on them. They have a duration on the edge associated with these event nodes. We have an ordinal time relationship here, so you can see that these blue events precede each other, and so even though there's no specific time encoded, you have a time relationship. You have things like timers, durations, time since, elapsed. You even have this sort of waiting for thing there at the top right? You have a time that has not yet occurred, or future time. And one of the thoughts is, well, maybe we can encode predictions or forecasts as structural elements, right? Associate them with a probability or maybe a slope or something that we can use. And then as time progresses, we can evaluate very quickly. We can query which trends are actually happening and in real time restructure our traversals according to the predictions that we're making as we're delivering output to our applications. Personally, I did that a lot with recommender systems, where we would encode recommendations as sort of predicted types of events. They would be embedded in the queries and displayed, and we would use clickstream data to reinforce that and to refresh the predictions using triadic closures or other triangle relationships. And so there's some graph things, right? These things are native to graphs. You can't do them in other types of domains that you get for free in these types of models. And the other thing I'm hoping to demonstrate both with this model and the Olympics model is that these multi-domain, right, where you have these vertices of different types and they're all sort of commingled in the same graph, that's actually going to be the path forward. That's what we're going to have to do in order to look at dynamics. So once we have time as a property, I think we all understand that time necessarily modifies traversal, right? It affects our queries. And so maybe we can check off the yes, this does speed up our query box, because rather than having to materialize some sort of time on demand and evaluate it against some criteria, we simply don't traverse that link, and maybe we eliminate a whole path of computation by using time to bound traversal. So traversals can exclude paths that are too recent or too old. You can actually weight by time. So if you want to minimize time, you can traverse. If you have options about paths to traverse, you can choose the minimum time, or you can choose minimum spanning trees that have the lowest amount of time with them. And like I said before, you can also add tentative or future times in order to create links that didn't exist before. So here's a quick example. This is an email mbox network. And so here I didn't include the link, unfortunately, but this is one of the first projects that I want to introduce, and it's called Tribe. So Tribe is a Python tool that will extract a graph from an email mbox, right? So something you can export out of Apple Mail or out of Google. And so this particular graph is a multi-graph where each vertex is going to be an email address, right, or an inbox, and the link, the edge, is going to be an email, right? And the properties are sent and the subject, right? And it's a multi-graph because two email addresses can have many emails between them. So I exported mine, and I got 6,174 email addresses that are in my inbox. I don't respond to that many people, so I'm not 100% sure where that came from. But 343,000 emails, right? That's how many emails are in this graph. And each of those emails has an average degree of about 111, right? So apparently these are people that I communicate with fairly often as I'm working. So that's too many. Right? Here is the hierarchical edge bundling version of that graph. So you can see that edges are collected together. So regions of color are a single email address, and the edges are the emails that are going across to other email addresses. And while this kind of looks neat, I'm not sure you could really make too much interpretation, right, or get too much insight off of this graph. So here's the first place where we're going to introduce some Graph Tool code. Graph Tool creates subgraphs by using views, right? So you're going to instantiate a view, which is a highly optimized layer on top of the original graph that doesn't actually remove any data structure under the hood, including properties and other things. So what I've done is I've created these filtering functions where you can supply before or after and the graph. And what it's going to do is it's going to return a closure, a function that takes an edge and returns true or false, whether that edge belongs in the view or not. So here, by specifying before or after, this inner function filters emails based on when they were sent. Another one that I've included on this slide that we're going to use here shortly is a degree filter, right? So excluding nodes who haven't sent a certain number of emails, right? So we could exclude anyone who's sent less than 5 emails. Or we could even create filters like there has to be two-way communication. So anytime I receive an email but I don't respond, exclude those types of nodes, right? And this subgraphing that we're going to be doing is sort of the constant thing that you're doing with these types of analytics, right? It's almost like predicates on a SQL clause. You have to do them or else you can't really understand or aggregate meaningfully. So once we apply these things, and you can see here's the view right down here, this graph view that's taking the edge filter and the degree filter, and we move down from 6,000 vertices to about 853 simply by filtering on all the emails that have occurred between 9 a.m. on August 1st and 5 p.m. on August 31st. So this is a month of emails, and you can see that the edge bundling gets far simpler to the point where you can even see the intermediate nodes, right? So those dots in the middle are root nodes that have, their control points where there's sort of critical massive communication. So in this case, most of those nodes are my various emails, like my Georgetown email or my DDL email or my Bengfort.com email. And then, friends and family are also in the middle there. So at this point, we now have the ability to conduct insights. Okay, so that's all great, and now we sort of understand how to get time into graphs, but what we actually haven't done is do anything with dynamics, right, which is the title of this presentation. So what are dynamics? Dynamics means change, and there are two methods to encode change in the graph. The first is to deliberately include time as a structure. Take it away from this property model and put it in as a specific element. And the second is to create a new data structure, which if you look at the math for this, is called it's a capital gamma, right? Capital G, dynamic graph, which is not just a single graph of vertices and edges, but it's actually an ordered series of graphs that increase in order of time. So the first thing that we have to then think about is if we're going to construct either static or dynamic graphs in this fashion, we have to, actually I can't think of a way that we could get away with, not doing some sort of discrete time, right? We need independent time steps. We need to identify this is one time region and this is another. And so, we can think of that in two ways. The first way that we can think of that is as intervals, right? So we have specified intervals of time, and intervals are independent. They can be fixed length, right? So an interval of an hour, or they can be variable length, right? So sequences of time where things are happening inside of events. But if you don't do that, you're going to have to pick some specific granularity for the time steps that you have. Either roll up or drill down, all the way from, like, let's say years, but I suppose if you have a really long graph, you can go higher than years. But going from years down to minutes, or, sort of depending on how fine timestamps you have, even down to seconds or milliseconds or something like that. And you have to aggregate all of your timestamps at one level, at one hierarchy. This creates an interesting opportunity that is for future work that we haven't explored, and that's watching how graphs change as we go up and down this hierarchy. And so if anyone's interested in that, they should look at that. But for this purpose, we're going to actually look at the week, right? So we're going to aggregate everything on week. So week 0 is, the week starting January 1st, and then week 1 and week 2 and so forth, all the way up to week 52. So here is the first mechanism, extracting time as an independent element. And anytime you see an edge with a property on it, that edge can simply become two edges with a vertex in the middle, right? And that vertex becomes the property. So that's a very typical way of expanding or even collapsing graphs, right? You can collapse intermediate nodes into single edges and get different levels of granularity there. So here, the weak is going to be these blue vertices, and you can start to see the different types of nodes that are connected to that. And what should immediately jump out at you here is this sort of linear ordering of events ordered by the alphabet in order to make that more clear. So A, B, C, D happened before J, K, L, right? And the layout here sort of specifies time from left to right as we might expect. And we can start to see things like B, E, and H are prerequisites to F, right? They have to happen before F. And that this entire system might not work without A and C kicking it off, right? These are the things that are generating timestamps. So that's method number one. Method number two, yes? So, I mean, it depends on the label. I haven't specified here. Oh, sorry. The question was, do A and C happen before or concurrently? Oh, I see. So the two times that are over each other. Yeah, I haven't really specified the relationship between those two times. But it's an interesting question. Yeah, absolutely. But I mean, and these are exactly the types of questions that you want these graphs to invoke, right? Is there concurrent behavior here? Is there some other behavior that we can see and investigate deeply? So I'm glad that that's the first thing that came to mind. The other sort of step that we can take is to grab subgraphs over time, and then at each period look at how the subgraphs changes. And so what you should note about this is that at each time step the edges are changing, the number of vertices are changing, right? So we get F in timestamp 2, we lose both A and F in timestamp 3, and here you can sort of really start to see the structure of the graph changing over time, although you lose information, right? It's hard to know what the relationship is between time T1 and time T3 without having that intermediate step in between. So I know I'm going a little long here, so I want to introduce this key phrases over time work that we did to investigate this topic. So another two projects that DDL is working on are called Baleen and Minky. Baleen is an RSS ingestion tool that just every hour downloads about 400 RSS feeds and grabs all of the HTML data from the web, stores it in a Mongo database. So far we've collected over 600,000 documents. It's been running since March 3rd. I sort of maybe said something to the effect of like, oh, 600,000 documents, 60 gigabytes, that's not that big, because I'm used to working on much larger things. But it's funny, once you actually start to grapple with this on like your single machine without Spark or something like that, it does feel pretty big. Minky is a NLP pre-processing tool that's specifically meant for preparing natural language corpora for machine learning. So producing document vectors and things like that. And so what it does, or what it's done on our behalf, is it's extracted a graph of key phrases weighted by their TF-IDF, their term frequency inverse document frequency score. And I think it's important to note that actually a graph representation is often the final product of a natural language analysis, especially if you're doing something like named entity recognition, entailment, reference resolution, things like that. A graph data structure gives you sort of an easy ability to analyze or figure out what's happening in the language. So the data model that we put together has 4 types of nodes, categories, so there's going to be things like politics, news, data science, feeds, those are the collection of documents that we're downloading over time, the document itself, which is actually what contains the timestamp of interest, the publication date of that article, and then we have all of these key phrases that are associated with it. And if you see, the first version of this on the complete corpus got us a graph of 2.6 million nodes and 46.9 million edges, which is about 20 gigabytes in memory, which is too much for this machine. So we sampled it down to about 139,000 nodes and 257,000 vertices. And hopefully you figure out that it's still pretty tough to work on that. Like any good data product or data analysis, we went through, that was the ingestion phase, and then we had to go through the wrangling phase. So one thing that we did here was to filter, again, create the subgraph of these high degree nodes. So if you guys remember that degree filter that I presented earlier, here we say that a node has to have 4 or more connections or edges in order to be allowed into our graph. And that kind of makes sense because we're eliminating, hapaxes or other phrases that may not have too much impact or weight on the things that we're looking at. This, if you guys aren't used to graph analytics, this is sort of the first thing that you should do with your graphs, and that's to make sure that you have a power laws degree distribution, which we do have, because that means that you're heading towards like a small worlds graph. You're heading towards a graph that has clusters and sort of meaningful. It's not just a fully connected graph that you really can't do much on. And then also looking at the distribution of your vertex types, right? You should sort of think, what is happening here, and what do we actually have in the graph. And then, so the last piece of the data wrangling is, again, this idea of the ego filter, right? And this is going to come up in both the static and the dynamic analysis, right? We have to somehow be able to pull out graphs or specific graphs for specific vertices. So again, this is another graph tool filtering mechanism where we create a function that returns a closure. In this case, we specify the vertex that we want to be the ego, the center of the network, and the number of hops out that we want to collect nodes for our subgraph on. And then we use the shortest distance between the ego and that vertex, and that's what we do compared to the number of hops to determine inclusion. And so you can see that if you take a single document, the title of this document is Villanova Outs Iowa, Exercises Second Round Demons to Reach Sweet 16. You can create an ego graph from that document and look at its key phrases specifically. So here are things like NCAA tournament, Super Bowl. That red vertex is its category. This is in the news category, not the sports category. Reaction, moment, poll. And so you can start to get a feel for what's inside your graph. And then the sort of smaller view is what the whole graph looks like. That's fairly unreadable. Yes. I'll get into that. And actually, that's the next topic here. So, what kinds of analytics, like graph-specific analytics, can we do? And the nodes are all different sizes, which was the question. How can we take a look at that? And so, the first thing that I think you want to start to look at is what is the centrality? What's the centrality of time here? So in order to do the static graph time as a structure style analysis, we have to extract at a certain level, right, this weak level. And you can see that the extraction here is simple. I mean, this is a lot of code, but I just want to point out that we're using this DT ISO calendar function over here to get out the weak number. So that's that aggregation, looking at that cut. And then here, we're just doing traversals, right? We're just looking for the neighbors and selecting nodes specifically for those neighbors. There are several types of centrality measures, and so just to highlight 4, you can think about things like degree centrality, right? The more connections a node has, the more important it has, which is in contrast to betweenness centrality. Betweenness centrality asks, well, if given all of the shortest paths from all nodes to all other nodes, which nodes sit in the middle of the most paths? And that's a very different idea than eigenvector centrality or PageRank centrality or CAT centrality, which think, well, it's not just about you, it's about you being connected to other important nodes. And what hopefully you can observe here is that the color is a scale color, continuous color, that the darker it is, the more important that node is. And the different centrality measures give you different metrics. And the questions that we want to start to ask is, well, how important are our time structures? Also, how important are our key phrases related to these time structures? So just to take a little cut here, and I really couldn't figure out a good way to visualize this, but to that graph, I've applied both betweenness centrality and CAT centrality and then ranked them. And so you can see we have both weeks and phrases, right? Because they're both vertices in the graph. So week 40 is more between than week 2, which is more between than week 45, which could sort of show that these weeks have more terms that are sort of more global, whereas we have a different ordering of weeks when you look at the CAT centrality. Then when you start to look at the terms themselves and their betweenness, you can start to see things like turnout, democratic, undocumented immigrants, big issue in week 45 versus in week 1, rose, local, pastry, dessert, lemon. But you start to see, like, it feels like there's actually sort of something connecting things here. In the CAT centrality, you can see citizen, monopoly, finance, big, efficiency, sweep, party, delegate, Twitter, comment, right? So these centrality measures, these things that we think of as graph-only type things, are allowing us to do an investigation that we couldn't have otherwise in fairly simple, like slide-level code, which is a good thing. So maybe graphs are something that we can use to perform analytics. What about dynamics? Can we look at the change over time? Well, to do that, you have to create sequences of time-ordered subgraphs. So here is week 2, week 4, week 5. What happened to week 3? Turns out that the server crashed on week 3, and so we lost all of the documents from week 3, or at least it didn't get anything. But the thing to note here is that the vertices are sized by their centrality, in this case, betweenness centrality. And they're sized globally, so they're not sized relative to the time, they're sized relative to all time. So what you can start to observe is that week 2 has fewer, more central key phrases as opposed to week 4, which has way more less central key phrases. And this is changing, this is fluctuating. So there's a news cycle, there's something happening that's changing the topics over time, right? Week 4, we're talking about things that we always talk about. Week 3, we're talking about things that we rarely talk about but are really important. And of course, you can animate this. And Graph Tool actually has an animation function, which I will display here. And you can start to see things. So I just want to point out a couple of things since I'm running out of time for animation. So as much as possible, you want to fix both vertex and edge positions. They shouldn't move. Transitions should be eased. So fade in, fade out. You want to sort of see what's coming and see what's leaving. The only change in animation should be time. Right? You don't want to change anything else. You don't want to change centrality, but you can animate any sort of property, but it should all be related to flow. And moreover, you should give the user control to explore change. Now, this isn't really available in Python, right? So Graph Tool uses GTK windows, so you can sort of give interactivity, and you might think there's interactivity with Jupyter notebooks or something like that. But with the size of these graphs, you can see that you're already in a huge performance drain as it is. So just to wrap up, I want to conclude with some thoughts about network visualization and sort of a contrast to how hard this might be. The most important thing, and hopefully what you're seeing, is that layout and positioning is by far the most important, and layout precludes you from having many nodes in your graph. So you need to create subgraphs. This is from Lane Harrison, and she talks about all these properties of graphs that you can change, that you can add elements to, particularly visual properties. And the reason I bring them up is because all of these things are available in Graph Tool. You can change the vertex shape, color, size, even give it pi nodes for edges. You can change the color, size, direction. So these tools are available to you, but the question is it enough? This is the complete key phrase graph ordered by week. There's not a whole lot of understanding that you can do in these things. And so you need to work on it. It needs to be interactive. You need to have a tool that you can go back and forth and specify different levels and modify it. And with that, I will leave you with this idea of visual analysis and graphs being essential for a visual analysis where there's a connection between the human and the analytical procedures, and challenge you guys to all go and look specifically at how you can create interaction inside of your analytics with the mantra, overview first, zoom and filter, details and demand. And if you can do that, I think that time and the dynamics of graphs will become a very powerful tool that you can use in your analytics toolkits. Thank you.